Thank you very much, Antonio. I hope everyone can hear me, but I guess so. So first of all, thank you very much to all of those who are still in the seminar this afternoon. I'm happy to present on my topic, the relevance of laser beam diagnostics in battery cell manufacturing. So my topic will be slightly based on beam shaping as well. So we have heard about that several times today. It will be also part of my topic today because there is a certain relevance. So skip the slide. So first of all, what we at PRIMES do. So we are developing and producing systems for the characterization of industrially employed laser beams as used in, for example, the automotive industry. We're still an independent and completely owner-operated player with now more than 140 employees, most of which are located in our headquarters in Pfungstadt, so in the Rhine-Main region, and a few colleagues in our subsidiary in Yokohama, Japan. So what we offer more than 30 years of experience in improving laser-based processes. So our portfolio ranges from laser power measurement and devices for characterizing the propagation of laser beams to integrated all-in-one solutions. We offer solutions for laser manufacturers through to the end users. And what we look for, so we're always looking for challenges. So challenges such as programming suitable software to answer all imaginable questions related to performance of lasers. So it's our laser diagnostic software. So why using lasers in welding? So other presentations might have answered this fundamental question already, but we often have a slightly different view of this process. So for example, precision. So laser welding is the method of choice for applications requiring a high degree of precision. Because of the low heat input, laser technology is the best method to weld highly sensitive components. And last but not least, the efficiency. The production of lithium-ion batteries is a very complex and sensitive process that involves very high material and energy costs. For this reason, the manufacturing process must be very efficient with high batch numbers at low cost. In order to take advantage of these benefits, it is crucial to check the laser performance in detail, not only at the manufacturer, but also during production. The advantages only become apparent when you know your laser. So skipping slides is still a little bit delayed. So I would now like to give 3 different examples of lasers used in welding applications. We will start with multi-mode, continue with single mode, and later on combine those 2 in core and ring assembly. First of all, I would like to point out a series of measurements for which we measured a whole series of machines. So all equipped with the same laser and used for the same purpose. We have performed direct fiber measurements of multi-mode lasers starting at 100 watt up to max power of 5 kilowatt. And as the fiber fills up with light, the calculated parameters change. So in this case, the direct fiber measurement means that there was no additional optic involved. So it was like the outgoing inspection at the laser manufacturer site. So therefore, this test is normally performed at the laser manufacturer, but we do that sometimes as an incoming inspection at our customer site as well. But for the following graph, so there it is. For the following graph on data cloud, we will now concentrate on power levels above 2 kilowatts. So we got rid of the 100 watt measurements. So even though we are now concentrating only on the power levels used for processing the material, the variation is very large and many data points are slightly outside the value specified in the data sheet. Each blue dot represents a full core measurement at 1 out of like 100 plus laser sources that have been characterized during this process. If you now take the additional influence of the processing head into account, you can see that things cannot get any better. Variations in quality or in the alignment. So in the alignment, like pollutions intensify this effect. So pollution, it could be like this, or shown on the image you can see right in the center of the slide. It can just be a dip in the power density distribution of the measured beam. This image is taken around +2 Rayleigh lengths outside of focus, because pollutions somewhere around the optical elements will not necessarily appear directly in focus, but typically out of focus. But it's not just the change in the beam distribution at this specific position in the beam path. It will most likely affect the thermal behavior of this laser. So it does make sense to measure that. The second example uses a single mode, so displayed in red, instead of a multi-mode laser. The advantages are quite obvious. So you can focus the laser down to a smaller spot and therefore achieve the same power densities at lower power and maintain the same Rayleigh lengths or the same working area in Z. So due to the use of longer focal lengths, you can process faster on even bigger areas. So there are even more benefits you can have with single mode lasers, but just to mention a few of them. But where there is light, there must be shadow as well. So the single mode lasers tend to develop astigmatism more quickly, like shown on the upper right side. It tends to cause higher degree of thermal lensing. On the lower right side, there is a graph coming from our software that just shows the shift of the focus position over a batch of welds that has been performed on a battery, for example. So it has been taken offline, but that is how the spot or the focus position can shift from weld to weld if you don't control that. And last but not least, more sensitive to alignment and the quality of optical components. So what we do see quite often in the field is that spot die or spot in focus are still quite round, but different kind of effects might appear around the focus. But 1 or 2 Rayleigh lengths outside of focus, you can see that in this specific example, I guess that the quality of the optics used, probably the collimation lens, was not probably chosen for this kind of laser. So different effects appear, which will result in changes over time or so. So let's jump into the next example and combine the best out of 2 worlds and have a look at structured or adjustable ring lasers. So conventional analytics, according to the ISO 11146 standards, using, for example, the second moment method, yield the focus position and the Rayleigh lengths. They are meant to do that on single round spots. In this example, we see that the structure of the beam is lost within less than 1 Rayleigh length. Therefore, we decided to define a further set of parameters for the analysis of ring beams. The structure focus is defined as the position with the smallest ring width, and the structure depth is the distance at which the width increases by a factor of square root out of 2. So we use the conventional definition of the Rayleigh lengths, so an increase in the area of the square root out of 2, but we apply it to the ring. So to obtain these values, we take cross-sectional profiles of the beam at several angles. So like shown in the lower right corner of the image. So furthermore, we can analyze the beam shape in terms of power distribution. In our example, you can see a distribution that has been generated using a DOE. So I just want to point out that in this specific case, 14% of the power is not within the main structure. So it's not guided in the core and not guided in the ring. This effect will not be present when using the cladding of a fiber to produce this kind of ring shape, and it can vary a lot. So you can see smaller numbers, bigger numbers, but it does obviously make sense to check for the power that is not within the distribution that was meant to be used for processing the material. So there will be other parameters that can be used to compare those lasers. At the moment, it is quite obvious that the standard methods will make a comparison impossible. So like mentioned by Gwen, it is like comparing apples with carrots. But that is exactly where we want to start. We want to make lasers comparable. So that is our challenge. So not only in my presentation, shaped laser beams have constantly been present, not only round and sometimes finely shaped, but finally, I would just like to point out that we can measure them all, almost. So I would like to close this talk with the two questions that came up in every single presentation. So what can we do for you? So we can make your laser beam comparable, that is one hand, and what you can do for me. So we need to set more sets of data as well as your experience to further improve our algorithms. So we have done a lot of work on measuring structured beams. It can be it is not limited to round beams. It can be any kind of beam shape. But without knowing the interaction between the laser and material and what is important about the structure that is measured, you can generate analytics to put numbers on that, but at the end that doesn't make any sense. So thank you for your attention and happy measuring. Thank you.